Today we're going to do fluid mechanics. And what we're trying to find is the coefficient of discharge in a tank filled with a partial amount of air and oil. The oil's specific gravity is 0.92 and the tank's height is 3 meters. We also have a jet, which is 1 centimeter in diameter. Our equation says that the coefficient of discharge times the area, the square root of 2 gravity times height and pressure over density should give us an answer. So first thing we're going to do is explain the diagram. Inside of the tank, we know that we have 25 kilopascals of pressure. We also know that we have the oil's specific gravity is 0.92 and the height of the whole entire tank is 3 meters. The jet is what we don't have right here. We don't have the area of the jet. So we're going to find that. We're going to take the coefficient of discharge to 0.72. And first, let's solve for the area of the jet. And how we do that, I'm going to take the area of the jet, I'm going to take pi r squared, and I'm going to say that the jet is 1 centimeter. And the only way I can get the true size of the jet's flow is to take 1 centimeter and times it by, multiply it by 1 meter. 1 over 100 meters. Squared.
Okay.
And we're doing engineering, so don't forget your units. Once this is all said and done, and you find your area for the jet flow, you can continue on to say that the jet's flow is going to equal to the exact same as the coefficient of discharge. This is just how you find the coefficient of discharge. So make sure you take that all in. The coefficient of discharge is equal to CD times A. I'm going to erase that. Now that we have our coefficient of discharge times the area, we can move on to say square root of 2g times height plus pressure over density. That's going to look just like this. Sort of a plug and chug type of method. So, what is G? G is gravity, or we can explain it in meters per second squared, because that's where we want to explain the gravity on the flow as it comes out of our jet. So we're going to say 2G, this part right here, would equal to 2 times 1 gravity in meters per second squared. So we're going to say 9.81 meters per second squared. Can you see that?
Yeah.
And then we're also going to say times that, multiply that by height, we're going to multiply that by height, and we all know what the height is right over here. The height is here, and the height is here, 3 meters. Over the pressure, and our pressure is 25 kilopascals.
It's plus. 3 plus. Yeah.
I'm sorry about that. It's 3 plus. It's our height plus pressure over density. And how do we find density? We find density by saying the specific gravity of all the oil as it flows through the jet. And our density is equal to the specific gravity, 0.92 times 1,000 kPa over meters cubed. Now, that's a lot to say, but in the long run, it's going to exactly equal to meters per second squared. But since we're doing engineering, we have to keep our units. Never forget to use your units. We're also going to times our specific gravity times 1 gravity in meters per second squared. Looks like a bunch, but it's really not. First thing we want to do is get rid of our units and bring them back later. We know that kilopascals and kilopascals sort of would take each other out of this, and then we're left with meters cubed, meters squared. So if we want to rewrite this, we can say 0.72, our coefficient of discharge. I'm going to rewrite that for y'all. Our coefficient of discharge square root of 2 gravity in meters per second squared multiplied by 3, which is our height, plus 25 over density. Our 25 is our pressure gauge in kilopascals, and we can say specific gravity times 1,000 times 1 more gravity. Now we have no units in the math, and we can sort of just work our way down to the next step. Once all our units is gone, it's sort of a plug and chug method. Now let's refer back to our diagram. You can see in the equation where we show for the pressure, where we show for the specific gravity, where we show for the height, and where we show for the jet flow. 25 kilopascals, specific gravity, 0.92 of the oil. The height is 3 meters. Coefficient of discharge, 0.72. And the jet flow is 1 centimeter in diameter. In this class we use a calculator, so I'm not going to go and do all the math longhand. I'll just show the next step. The next step would be to start at the lowest point inside of the square root bracket. Oh, I've already done it. I've already done it. So for most people who take structural mechanics or fluid mechanics, there will be a calculator given in class. So once we have all of our values, plug them into a calculator as seen, exactly as seen, and your answer should look something like the coefficient of discharge, Q, equals 6.02 or, and never forget to use your units, meters per second squared, or, because if you refer back up to here, we knocked some of the kilopascals out of each other, and we were left with meters per second squared. We had a meters cubed, and you know, exponential values, there's an invisible 1 there. We can get rid of the meters per second squared and say meters. Let's say meters cubed per second.
Okay.
Once again, if you need any help or any questions about fluid mechanics or structural mechanics, just leave a comment on the video. Thank you for watching.